So, as we discussed it earlierly, so for three-dimensional body there exist three stresses and three strains. So there are for three-dimensional body we are having six stresses and six strains. So here I am having three axial stresses sigma x, sigma y, sigma z, and three shear stresses tau x, tau y, z, and tau zx. So the stress and strain relationship matrix is D matrix. Okay. So where the D matrix is known as stiffness matrix, now we are going to try to derive the relationship matrix D. Okay. So see, so from Hooke's law we can write that strain is equal to stress by Young's modulus. Strain epsilon is equal to stress by Young's modulus value. So here, since for one dimensional body there exists only strain in one direction, so I can consider to take the equation epsilon is equal to sigma by E to derive the strain. Okay. So if you consider three-dimensional body, so for three-dimensional body, to determine the true strain produced in x direction, I am utilizing the equation sigma x by E minus mu into sigma y by E minus mu into sigma z by E. So mu is nothing but Poisson's ratio. Okay. So see, if I considered a three-dimensional element, so whenever the load is applied in one direction, corresponding to that the strain will be developed in other directions also. Okay. So see, if I consider a plane like this, if I consider plane element like this, okay. So this is the plane element, 2D element, assumed to be 2D element. So now if I apply the load in the x direction, then what happens? The body will be tends to elongate. So whenever the body elongation will be takes place, the height of the body is going to be reduced. So that even if you apply load in one direction, the strain is generated in this y direction. If even you apply load in x direction, the strain will be generated in the y direction also. Correspondingly, if I consider three-dimensional body, even if I apply the load in one direction, the load is applied in one direction, the strain will be produced in respectively other directions also. So here I am converting the total strain which is developed in y direction and x direction into y direction, z direction into x direction by multiplication of product of Poisson's ratio. Okay. So now I can take it as sigma x by E minus mu into sigma y by E minus mu into sigma z by E to determine the true strain in x direction. Similarly, to determine the strain in y direction, I can take it as sigma y by E minus mu into sigma x by E minus mu into sigma z by E. So correspondingly, I can take epsilon z is equal to mu sigma x sigma z by E minus mu into sigma x by E minus mu into sigma y by E. So we know that shear strain is equal to shear stress by modulus of rigidity G. So therefore, tau yz, gamma yz can be written as tau yz by Z, gamma xz can be written as tau xz by Z, gamma xy can be written as tau xy by Z. Okay. So this the relation between the strains and stresses when which are induced in a three-dimensional body. Okay. So we know the relationship between the Poisson's ratio, Young's modulus, and modulus of rigidity. I can write it as G is equal to E by 2 into 1 plus mu, which gives the relationship between the Poisson's ratio, Young's modulus, and modulus of rigidity. Okay. So from these three equations, so from the equations of epsilon x, epsilon y, and epsilon z, I can write the function epsilon x plus epsilon y plus epsilon z as, so 1 minus 2 mu by E into sigma x plus sigma y plus sigma z. Let this be equation number 1. So now I am considering only the function of epsilon y plus epsilon z. So if I consider only function of epsilon y plus epsilon z, I can have the function as 1 minus 2 mu by E into sigma y plus sigma z minus 2 mu into sigma x by E. Now keeping the respective of sigma x by E only in this at one place and transferring the remaining functions to the epsilon y plus epsilon z, then I used to have sigma y plus sigma z equal to d by 1 minus 2 mu into epsilon y plus epsilon z plus 2 mu by 1 minus mu into sigma x. Okay. So by solving substituting in the equation of epsilon y plus epsilon z functions in this equation, finally I used to have the sigma x as e by 1 minus 2 mu into 1 plus mu into 1 minus mu into epsilon x plus mu into epsilon y plus mu into epsilon z. So this is the equation, stress equation, stress and strain equation for three-dimensional body in x direction. So similarly, I can derive epsilon y plus sigma y and sigma z. Whenever we want to determine sigma y plus sigma z, I have to consider the x and z strains functions. And similarly, sigma z, if I want to consider, I can sigma z. I have to consider the strain in x direction, strain in the y directions only. Okay, so we know the Poisson's shear stress tau xy is equal to G into gamma xy. So G is nothing but Poisson's ratio, modulus of rigidity. In the place of modulus rigidity, I am representing it as E by 2 into 1 plus mu into gamma xy. Okay. To convert the E function E by 2 into 1 plus mu as a function of E by 1 minus 2 mu by 1 plus mu, and then multiplying in the numerator and denominator with 1 minus 2 mu. So if I convert into 1 minus 2 divide by function as divided by 1 minus 2 mu, so see e by 1 minus 2 plus 1 mu into gamma xy, I am taking the product of numerator and denominator with 1 minus 2 mu. So if I am multiplying that, I used to convert the function as e by 2 into 1 plus mu into 1 minus 2 mu into 1 minus 2 mu into gamma xy. So dividing the function of 1 minus 2 mu with 2, I can have the function as 0.5 minus mu into gamma xy. Correspondingly, I can write tau yz and tau xz. So if I substitute all these equations, 6 equations in the form of a matrix, then the stiffness matrix can be obtained as E by 1 plus mu into 1 minus 2 mu, and function is 1 minus mu into mu 0 0 and zeros, and rest of elements are zeros with the product of epsilon zeros. This function is known as stiffness function of the three-dimensional element. Okay. So correspondingly, I can determine the stress and strain relationship for the two-dimensional body. Okay. So in two-dimensional body, there exist two conditions. One is plane stress condition, and second one is plane strain condition. Okay. See, this is the relationship matrix for the plane stress condition. Sigma x, sigma y, tau xy, E by is equal to E by 1 minus mu square 1 mu 0 mu 1 0 0 0 1 minus mu by 2 into epsilon x epsilon y plus epsilon z. So see, what is plane stress means? The plane stress is defined as state of stress in which the normal stress and shear stresses are perpendicular to the plane are assumed to be 0. So example of this is thin plate. Okay. So if I consider a thin plate like this, and some force is applied on plate. Okay. So if the force is applied on the plate tends to enlarge its diameter. So that means the deformation is produced in x direction, deformation is produced in y direction. So when the plate enlarges, the diameter thickness of the plate is going to be reduced. Okay. So whenever the dimension is changes means the strain will be developed in that direction. So in the strain is developed, correspondingly the stress also develops in the particular direction. So but when compared to the deformation or stresses developed in x direction and y direction, the z direction stress is very less. Hence, we are assuming that the stress in z direction is assumed to be 0, and similarly the stress in yz plane and shear stress in xz plane is also considered to be 0. So such type of stress conditions is called as plane stress condition. Similarly, plane strain condition. In plane strain condition, we are assuming it is said to be a state of strain where the normal strain and shear stress are assumed to be 0. This is the equation that relates the stress and strain for plane strain condition for two-dimensional body. So that is sigma x, sigma y and tau xy is equal to E by 1 plus mu into 1 minus 2 mu, 1 minus mu 0 mu 1 minus mu 0 0 0 1 by 2 minus mu into epsilon x, epsilon y and epsilon z. So examples for the plane strain condition two-dimensional body is cube long cylindrical structures which acts under cylindrical pressure or internal pressure. Okay. So these are considered as as I said, you are having two states of condition for two-dimensional body. plane stress case and plane strain case. So plane stress case will defines the stress in the z direction is assumed to be 0, shear stress and shear axial stress in z direction should be assumed to be 0, and plane strain case, strains are assumed to be 0 in x direction in z directions. So that may be axial strain or shear strains are 0 in the z, assumed to be 0 in z direction. So here 0 means that it never states that the strain or stress developed in that particular direction, there is no strain or stress in that particular direction. Only the 0 defines the stresses which are developed in the particular stresses or strains which are developed in that particular direction are negligible, only negligible condition. Okay, so so this is about the stress and strain relationship for 3-dimensional body, 1-dimensional and 2-dimensional body. So we used to continue in next class.